From the fabulous room 1065, it's the Kelvin Dueck Show of Physics, and we're live.
So this is lesson 3. Remember I said we were going to skip lesson 3. We did lesson 2, lesson 4. Now we've done lesson 3, going backwards. Okay? Pardon me? Did you guys pass the handout down that I gave you guys? Did I give you guys the handout? Did I miss your row? No, we'll just pause. So in Math 10, you learn 2 different ways to graph a line. Actually, you learn 3 different versions of the equation. Don't write this down. Don't write this down. There's the stupid version that we call standard form, which looked like this. Or general form. I hate that version. It's useless. I don't know why we emphasize it so much. There is only one way that it's at least somewhat helpful. It's somewhat handy if instead of having it equal to 0, you minus that number over, and you can do some math in your head and solve for x, I guess, but meh. The second version that you learned, don't write this down, was what we called slope point or point slope form, which looked like that. By far the most useful version of an equation. Those of you that take calculus next year, you'll find that becomes your best friend, because one of the things you'll be doing in calculus is you'll be finding, listen close, the equation of the tangent line. Well, to do that, you need to find a derivative, that's a calculus term, and one point. And then you can just plug and chug in calculus. It's much nicer than trying to do the rest of it by hand. But what we're going to use this year is slope-intercept form. So now you can pick your pencils up. First, we defined slope last year as something over something, 2 R's. Okay, we defined it as the rise over the run. Sometimes you'll see it written as delta y over delta x. I rarely wrote it that way last year in my Math 10. I often write it that way in upper level physics because it's the shortest one and I'm lazy. Oh, who remembers what does that little triangle mean? And I called it a delta, which is what we call it in science. What does that delta mean? Sorry? Change in. What's change in anything? I snuck this into my Science 10s, and I think I know some of the Science 10 teachers did. If you forgot, that's fine. Does anybody know what change in anything is? When you see that delta, what it really means? It really means final minus initial. But in this case, instead of using final and initial, we wrote it like this. The second y minus the first y. Remember the slope equation or the slope formula? It's actually contained in that middle short one there if you know that change in anything is either final minus initial or second minus first. So of the 3 versions of slope, Kyle, this is the one that long ago I committed to memory because I can go that way or that way. Either way is just fine. Okay. And we taught you how to graph. You learned how to graph. So number 1 says graph the following on the grid to the left. First of all, look at those 4 equations. How can you tell instantly just by glancing at them that none of them are curves? Ooh. What, Kai? No exponents or square roots or weird stuff. You know what? No weird stuff. They're lines. My favorite is people say they're straight lines. A line has to be straight, but that's why it's called. Anyways, we'll leave that alone for now. I always like to know what I'm trying to graph. Who's in grade 12? You guys did pre-calc last year? So for you guys, and for those of you who are in grade 11 preview of coming attractions, don't write this down. As soon as you saw an x squared, you instantly knew what shape was that. Do you remember? Yes, parabola. Gotta be. Okay. The more math you take, the more of these little hints you pick up. I know that if I see an x cubed graph, I call them John Travolta graphs because they look like this or they look like this, and I do the stupid little John Travolta. It's a dumb way to remember. They're odd degree functions. I also remember it because John Travolta is very odd. They're odd degree functions. Whatever dumb trick I come up with. Gradually, the more math you take, Jeff, the more different graphs you'll have at your fingertips, and you can kind of take shortcuts. We always start out with the straight line because it's where everything else comes from. So, number 1, is in slope-intercept form. How do I know? Slope-intercept form basically said, yeah, the y, what? By itself, which it is. Now I have to remember what everything meant. I'm going to come back to this number in front of the x later, but the first thing, if I'm graphing, and I know it's a line, no exponents, I always look for the constant term, the number that came after the x. What was that negative for? What did it tell you? This is the y-intercept. And what that meant is you would put a dot at -4 on the y-axis. I don't know, maybe I should make you put those down. Okay, I'll let you wear them up there. Juan, what's the number in front of the x? What is this number? What does this number here tell me? The fraction or the number or the decimal in front of the x? Slope. Dane, what is the slope? Can you just read it to me out loud? Read me the fraction in front of the x.
Oh, y.
No, the fraction.
Oh, sorry,
Say that again, please.
2/3.
Did you hear what he said? Not x. I didn't. No. I cut you off on purpose. What's the fraction? What's the slope?
2/3.
And the way he says it, 2/3 tells you how to count. It's up to over 3. Starting from the y-intercept, you're going to go up to over 1, 2, 3. Up to over 1, 2, 3. Up to over 1, 2, 3. You always go over to the right if there's room. What told me to go downwards instead of upwards? When did I go downwards instead of... If there was a negative slope. Okay. And those is the parabola, the negative also had an effect there too. It kind of all starts to tie together. You're like, oh, they actually overlap quite a bit when it comes to... And I can go backwards, Trish. Back 3, back 2, back 3, or down 2, back 3, down 2, back 3. You guys have rulers. I have a really, really tough time using a ruler on this tablet. I'm going to try, but it's really, you know what? I'm going to cheat. Where's my insert or draw? That's what I want. A line with, connect the dots. Wow, that's not quite what I wanted. That's in a highlighter. I need to change the pen properties. Pen, let's go dark purple, sure. Let's go a little thinner. Okay. Hey, that's better. There you go. What do the arrows on the end mean? Okay. Now, we're going to have to be careful. In physics, they sometimes won't be, because in physics, we're not going to be talking about x and y. We're going to be talking about stuff. And so you may have to think for a second and say, actually, can this ever be negative? Time, for example. I'm sorry, time's not negative. I saw Einstein once said, no, we're not going backwards in time. Time's going to be positive. In fact, in physics, most of the time, we're going to be dealing with the top right quadrant, quadrant number 1, most of the time. But let's keep going here. 2, I'll do 2 in red. It's in slope-intercept form. What's the y-intercept? Positive 5. What's the slope? As a fraction, what's in front of the x? Negative 2 over what? It's invisible. Okay, negative means down. Down 2 over, always to the right, 1. Down 2 over 1. Down 2 over 1. Down 2 over 1. And I can go backwards. All right, let's try this again. See if it works. I know it's way off. Have patience. Oh, use the mouse, Mr. Dueck. It's believe it or not, my laptop is doing a fair bit of heavy number crunching, which is why it skips there, and then it slowly sets aside the memory. Okay. Oh, I said I was going to do it in red. Pen properties. How about red? There you go. This third one is going to show up a fair bit this year. What's weird about this third example? Dan?
There's no slope.
I got to be really, really fussy. Technically, there is. First of all, what's the obvious? What's missing? What? One variable. What letter? What's missing?
The x.
Okay, there's no x, which means it's not that there's no slope. What number in front of the x would make the x vanish?
0.
Okay, the slope is 0, which is different from no slope. I got to be fussy. What's the y-intercept, though? -8. So this is still, I'll go green. This is still a y-intercept of -8, which means down right there. What did you say the slope was? Not no slope. As a number, it's what?
0.
What does the slope of 0 look like? And don't say a straight line, because all lines are straight. Use a different word. Horizontal line. Okay? That one I'm just going to freehand. Close. For me, that's pretty good. This graph has a nickname, this horizontal line. This is often called the constant graph. It shows up in physics often if you're graphing something and that something turns out not to be changing, or the fancy word for not changing begins with the letter C, chi, is, if something's constant. So if you see a graph like that, you can, it's constant. Those of you in Science 10, when we did velocity, time, and distance velocity graphs and all that, horizontal line meant that your distance wasn't changing, you weren't going anywhere. Your velocity was 0. What about graph number 4? What's the y-intercept of graph number 4?
0.
0. This line goes through the origin. Many of our graphs will, not always though. In fact, one of the questions we'll ask ourselves, Tawny, is should this go through 0, 0 or not? If it goes through 0, 0, I'm saying that when there's 0 of my input, there's 0 of my output. Maybe not. So this has a y-intercept of 0. I'll do this one in black. And it goes down 1 over 2, down 1 over 2, down 1 over 2. Okay. That's generic math. Now I need to talk specifically about graphs in science and in physics. So usually in physics, we're going to be graphing in the first quadrant, since most of the time we'll have positive value data. And these are the rules for any physics graph, Jeff. On your test, on your quest, the last question is going to be, I'm going to give you some data. I'm going to say, graph it, please. And you need to make sure to get full marks that you follow all of this. You going to make it, Shaq? Because that was a mighty long blink. It's one of these. Ah! Nothing? Kids at home are freaking out online? Okay. It says, draw and label the x and y axis in the following form. So what you have to do for me, you have to label the axes. You got to tell me what you're measuring. And what I mean by that is you're going to tell me what it is, comma, the abbreviation you're using, and the units. Distance, comma, d, meters. Time, comma, t, seconds. Momentum, comma, p, you don't know this yet, kilogram meters per second. Momentum comes later. Oh, little note, time is always on the x-axis. That's a fib. Time is always on the x-axis except for the one activity that we'll be doing where it's going to be way easier to put time on the y-axis, but I'll tell you then it's clear. If you're not sure, time goes on the x-axis. Okay? So, first thing, make sure you label the x and y-axis. Kids throw away marks. They give me a graph, but they haven't told me which one's x and which one's y. I don't know if they graphed it right on the test. Select an appropriate scale and label it. Try your best to have the graph fit as much of the page as possible. In other words, if you have a piece of graph paper like this, don't write this down, don't give me a graph that big. Change your scale. Here, instead of going up by ones, maybe you should have got up by 0.1s or something like that, because you only went that high. You can go higher. Change your scale. Here, maybe you should have gone up by, or the other one I'll see is a graph like this. 1 point, 2 points. and then something over here. Okay, shrink your scale down. Pick a good scale, and I'll walk through how we do that. But pick a good scale. Your scales don't have to be the same on each axis. You can go up by 5s vertically, and you can go up by 2s horizontally. Doesn't matter. But pick a convenient scale. I would not go up by 7.3s. That would be just awkward to keep track of. That'd be dumb. 1s, 2s, 5s, 10s, 0.1s, 0.5s. That's pretty much it. Once in a while, I'll go up by 3s, only once in a while. Common mistake number 2. Kids forget to give the graph a title. The easiest title is whatever's on the y-axis versus whatever's on the x-axis. You can make up better titles than that. Graph of car rolling down a ramp. But if you're not sure, distance versus time title. Okay. Turn the page. Plot the points. If we have a measurement with some amount of error, now the equipment that we're going to be using is not going to have as part of the equipment the error tolerances. If we did, I'd teach you about error bars and circles and saying, well, I know that although I'm putting my point there, I may be putting my point right there, I'm pretty sure it's somewhere in this area, and you can figure it out from how bad the equipment is. We don't have that technical kind of equipment. So even though it says if it has measurement, some errors, draw a circle or cross, we're not going to be doing that. If your data points look as though they are in a nice straight line, draw the best straight line that averages the data. What did I underline here? What did I underline here? Read it to me, Manny.
Do not draw freehand.
Use a what? Is that why I handed some? Yeah. Okay. I'll take marks off if you freehand. You freehanded. It's very tough for me to actually get a ruler on this slippery screen and have it stay in place, but I'll try to once in a while. Then I'm going to look for the equation of the line. I want you to determine the equation. How? First thing you're going to do is you're going to find the slope. Pick 2 points on the line. Two points that are fairly far apart. Don't pick 2 points right next to each other because you may have made an error and it won't show up as easy. Find what's delta y an abbreviation for, begins with the letter R and rhymes with I's. The rise and delta, find the rise, find the run, find the slope, rise over run, delta y over delta x. Show these calculations on the graph somewhere, please. I'll be looking for them. So show me what points you use, clearly mark what points that you used, make them stand out. You can draw the little slope triangle if you want to. It's up to you, but make it clear. Okay? Use appropriate units for slope. I wrote here, keep in mind sig figs. I'm not going to be fussy on that. Find the equation of your line using y equals mx plus b, where don't use y and x. Use whatever letter you put on the y-axis. Often it will be d for distance or v for velocity. And don't use x. Use whatever letter you put on the x-axis. Often it will be t for time or m for meters or distance or whatever. So as an example, d equals 3.4t plus 8. A little comic, so I think we should give it another shot. We can break up and I can prove it. Here's a lovely graph of our relationship. And you can see the slope is going down. The man says, huh, maybe you're right. She says, I knew data would convince you. No, I just think I can do better than someone who doesn't label her axes. You'll notice the graph doesn't have a title. Axes aren't labeled, no scale. Guys, you can do better than that. Ladies, you can do better than that too. Sorry? Yeah. Oh, our relationship? Good point. The graph has a title, but no scale, no labels. Let's try one. Okay. It says, graph the following data and analyze the graph by finding the equation of the line of best fit. Say, what? So we were measuring a car rolling down a hill. And here's the data that we got. At 2 seconds, our little radar gun said the car was traveling 5.4 meters per second. At 4 seconds, it was traveling at 7.8. At 6 seconds, it was traveling at 10.2. At 8 seconds, okay, there's our data. Let's make a graph. What do we put on the x-axis unless they specifically tell us not to? Always. So I'm going to go like this. Time, comma, t, seconds. What's going to go on the y-axis? Velocity v, comma, meters per second. All right. Let's give our graph a title. How about velocity versus time graph? That's a pretty blasé title, but that'll get you there, always. You can be more creative than that if you want to, Halen, but there you go. You can always go y-axis versus x-axis. Okay. Darian, what's the smallest time value that appears in my chart? What's the biggest? So I need to be able to fit both a 2 and a 10. How many squares along the bottom? Count? Yeah, you have to count. Sorry, how many?
24.
24? So if I need to fit at least 10 things and I got 24 squares, what would be a good scale to go up by if I want to use as much as I can? .5 I don't think would be good. Oh, sorry. I see what you're saying. Yeah, I think every 2 squares should be 1 second. So yeah, 0.5, because that would use up 20 squares of the 24. Does that make sense? Now, I'm not going to label the 0.5s because I notice there's no decimals in my time. I'm going to go like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's a good scale. Going up by ones, only using half the graph paper, Tawny, I'd probably take off a mark or a half mark. No, we can do better. What's the biggest velocity value that appears in my graph? So how many squares vertically is it? Yeah, count. Can we go up by halves? Can we go every 2 squares is 1 here? Or how many squares is it vertically?
24.
Oh, 24. I got to fit 15. I guess the best I got is I got to go up by ones. Because I can't somehow go up by 2s and fit 30 in there, right? So now, I don't want to label every square. That's going to be really confusing. So I'm going to go up by ones, but I'm only going to label, Jake, every other square. I'm going to go like this. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So how we got that okay, Shaq? Okay. Now I'm going to graph the points. I'm going to change colors. I'm going to go red so it stands out. The first point, what's the time value? 2 seconds. What's the velocity? 5.4. I got to eyeball it. 5.4 is going to be, well, 5 is halfway between 6 and 4. 5.4 would be halfway to halfway of the 6, kind of roughly. Yeah, it's going to be, I think, about there-ish. Yeah? Close. Darian, what's the next point?
4 seconds.
So 4 over 7.8, just below 8, yes? Zach, what's the next point?
6.
So 6, a little bit bigger than 6 over, and a little bit bigger than 10? Right?
Yeah.
Trevor, what's the next point?
8 and 12.6.
Okay, 8 and 12.6 is going to be a little bit closer to 13 than to 12, but not by much. Really, it's going to be about halfway because that's about as accurate as I can be on this scale on rough graph paper right now. You know what? One of my points is in the wrong place, isn't it? And I can tell because my distances aren't equal. I think I need to take this little guy here. I don't want to do that. I need to move him. There. I accidentally put him at 6.5 seconds or something like that. And the advantage with graphing, Dane, is our brains are much better at spotting visual patterns. Like I noticed something looks wrong, even though I didn't notice the counting part. What's the last point, Dane? 10, 15. That one I can get exact, I think. 10, yoink, 15. Is that right there? Do these look linear? That's a fancy word for saying, do these look like they're in a nice straight line with each other? I don't think this is a curve. If I'd gotten points that kind of looked like that, then I'd think maybe it was a parabola. Those of you that have done Math 11 are a curve, but looks linear. Does it look like it goes through 0, 0? I don't think so. So I'm not going to force it to. What I'm going to do is I'm going to lay down my ruler and do what's called a line of best fit. Now, what does a line of best fit look like? You try and go through as many points as you can. If you can't go through every single point, you want to have the same number of points above your ruler as below your ruler. So if you got 1 point above your ruler, try and also have 1 point below your ruler. There is a better mathematical way to do this called least squares analysis regression. Meh, we're just going to eyeball it. So for me, with my ruler, I kind of sort of like that-ish. I'm a little high. Let's try that again, Mr. Dueck. These are made-up values, and they do seem to work very well. You're going to find often you'll have a couple of points that just don't want to fit in very well. That's just noise in the data. That's better. In fact, I look like I have a y-intercept of approximately what? For me, yours might be a bit different. Some of you might have got the same. Some of you might have a y-intercept that looks to be about 2.7 or 2.8 or 3.1 or 3. And that's fine. We're doing a rough line of best fit here. Okay. A says, what is the y-intercept? Now, if you have the same y-intercept as me, great. Otherwise, you'll write down, McKinley, what your y-intercept is. So my y-intercept is 3. What does it mean? What is the y-intercept telling me? The fact that this graph goes through 3 high at time 0 based on what I've called each axis. What is that?
The original was
Darian, you're right. What?
starting speed.
Do you remember what fancy schmancy word we used in Science 10 instead of original or starting? Beyond the letter I. Initial. You know what? This is V initial. It's the initial velocity. When you started the stopwatch, Zach, you were already moving at 3 meters per second. Now, I also said I wanted you to analyze the actual equation and slope. So we're going to do that, and I think we're going to do that on the graph paper, kind of right down here. We got some room here. So first of all, let's find the slope. And I'm going to go with a slope between that point and that point. They're nice and far apart, and they happen to be on grid lines. The fancy word for that is lattice points. Here is what I wouldn't use. I would not use this point right there because it's hanging in midair. I don't know how, I can't be accurate with that. I would not use that point right there because it's hanging in midair. I'll try and find somewhere a lattice point where it's going through a grid. So now that I've done that, what's the slope? What's the rise? How high is my top point? How high is this guy? How low is this guy? How low is this guy right here? 3? There's my rise, right? Change in height. What's the run? Now I go down. How far right is this guy, Shaq? You said it already? Minus, how far right is this guy? 0, conveniently. So it looks like I'm going to have a slope of 15 take away 3, 12 over 10. Now, in math 10, we wanted it left as a fraction. In physics, please decimalize it. So what is 12 divided by 10, please? I think 1.4? 1.2, that's what I said. There's the slope. Now let's actually find the actual equation. Oh, it says what are the units of the slope for part B and what does the slope represent? So first of all, the slope is 1.2. 1.2 what? Well, what are the y units? What are the units on the y-axis? Over. What are the units on the x-axis? It's meters per second per second. Or, what did we call that in science 10? Do you remember? It's meters per second squared. Oh, you know what? What was meters per second squared? What does the slope represent here? Right? Right? Now, I still haven't actually written out the equation, and I forgot to ask you to do it in this part, but I did say you were supposed to find the equation in our what does every graph have? So we're going to write the equation over here. The equation looks like this. Normally it's y equals mx plus b, except I don't want to use y. What letter did I put on the y-axis? V equals m, slope. What was the slope? 1.2. Not going to write x. What did I put on the x-axis? T plus, what was the y-intercept? There is the unique equation to this graph. This equation, this graph, has the equation v equals 1.2t plus 3, where 3, the y-intercept, is vi in this case, and the slope, 1.2, happens to be the acceleration. How did I figure that out? I looked at the units and I scratched my brain a little bit. So we're going to work on this for the remainder of class, and you'll get some time next class. It says this, assignment. Record and measure the thickness. Did I include graph paper, by the way, in this or not? Yeah. I did? Okay. I photocopied extra in case you botched the first one. You're going to measure and record the thickness of 50 pages in a textbook, 100 pages, 200 pages, 400 pages, 550 pages, and 700 pages. I would make up a chart like this. Pages, thickness. Okay? And then you're going to set up, you're going to graph number of pages on the x-axis versus thickness in the y-axis, and I would do thickness in millimeters. Otherwise, you'll be getting lots of decimals, and it's yucky to work with. Then you're going to find the slope and the equation of the line, and then you're going to use your equation to calculate the thickness of 225 pages and 1,000 pages. Now, if you're not sure how to do that, we'll get to that next class. Now, let me just hit pause for a second here.